Okay, let's jump right into this explainer. Today, we're unraveling how a seemingly innocent parlor puzzle from the 1850s morphed into this profound mathematical mystery. We're looking at the classic n-queens problem, the old chess brain teaser. But we're going to explore how it slowly transformed into an absolutely rigorous mathematical frontier. It's honestly a fascinating story, right? It perfectly bridges the gap between old-world parlor tricks and the absolute cutting edge of modern computer science.
So how exactly does a chess puzzle from 1850 end up breaking the minds of modern artificial intelligence? Well, we're exploring a mystery that stumped mathematicians for over a century, and it's now literally used as an obstacle course for modern AI. The classic puzzle is simple enough. How do you place a certain number of queens on a board so none can attack each other? But back in 1850, a much more devious variant was posed. It asks, if someone else starts the puzzle for you by placing a few queens on the board, can you guarantee that you can actually finish the whole thing? This is the completion problem. And as you'll see, the answer has huge implications for how we measure the problem-solving logic of AI today.
To appreciate how wild this evolution really is, let's quickly hit the timeline. We start in 1848. That's when a German chess composer named Max Bösel published the original 8 queens problem. Just 2 years later, in 1850, Franz Knock drops the much harder completion variant. And then, well, pretty much crickets. Literally over a century goes by with incredibly slow progress. It wasn't until 2017 that things suddenly kicked into high gear when researchers Ghent, Jefferson, and Nightingale identified this completion problem as NP-complete. That was a massive revelation for AI research. By 2021, a team led by Stefan Glock established linear mathematical boundaries for the puzzle. And just recently, in 2026, Hugo Møller Nielsen absolutely shattered those bounds with a brilliant new proof.
This original setup brilliantly illustrates the core conflict we're talking about. In Nauck's 1850 challenge, he placed just 2 queens on a standard 8x8 board, one on b4 and one on d5. The question was, can you add 6 more queens to achieve a full 8 queens configuration? Sounds pretty straightforward, doesn't it? But here's the catch. Mathematically speaking, those first few placements dictate absolutely everything that follows.
Okay, so the crucial concept to grasp here is the n-queens completion threshold. Think of this as a mathematical point of no return. It's the moment you risk painting yourself into a corner. Mathematicians call this threshold QC of n. In everyday terms, just imagine you have a giant chessboard, size n. You start blindly dropping queens onto it, making sure they aren't currently attacking each other. The completion threshold is the absolute maximum number of queens you can drop this way, and still be 100% guaranteed that a solution actually exists. Stay at or below this number and you're golden. The puzzle can definitely be completed. But the second you cross that threshold, you enter a danger zone where the board might be fundamentally unsolvable.
The real danger of blind placement is this. If you place too many queens randomly, you will inevitably hit an algebraic deadlock. The remaining pieces simply run out of valid squares. You see, the standard mathematical solutions for placing these queens rely on very strict algebraic equations. They are incredibly rigid. Because of that rigidity, placing even a few queens randomly can instantly invalidate those mathematical constructions, essentially forcing the remaining pieces into a corner. And this deadlock isn't just about running out of physical space. It's about those overlapping lines of attack, the rows, columns, and diagonals creating a tangled web of conflict that mathematically just cannot be resolved.
Now, to actually solve this mystery, modern mathematicians had to get super creative. They translated the physical chessboard into a highly abstract concept called a bipartite graph. Researchers like Glock and his team basically stripped away the familiar checkered squares and turned the whole game into a pure graph theory problem. They split the board into 2 distinct groups of nodes. One group represents the rows, and the other represents the columns. So, those physical squares on the chessboard, they simply became the lines or edges connecting a row node to a column node.
So, to wrap our heads around this graph, let's imagine a complex, color-coded dance where the rules for who can partner with whom are ridiculously strict. The real genius of this approach is how mathematicians handled the diagonal attacks of the queens. They actually didn't use nodes or edges for the diagonals. Instead, they treated the diagonals as colors. Think about it. Every single square on a chessboard is crossed by 2 diagonals, right? One slanting up, one slanting down. So in our graph theory dance, every connection between a row and a column is assigned a specific set of 2 colors that represent those exact diagonals.
By looking through this new lens, the rows and columns become partners joining hands, but the diagonals act as colored outfits that no 2 couples are allowed to match. Let's break that down.
If you place a queen on a square, you're essentially selecting an edge between a row and a column. Since queens can't share rows or columns, each node can only hold one hand. And because queens cannot attack diagonally, none of the joined couples are allowed to wear the same colors. So in graph theory terms, finding a valid n-queens configuration is exactly the same as finding a perfect rainbow matching in this heavily color-coded bipartite graph. It's a brilliant visual analogy, and it finally allowed mathematicians to use incredibly powerful probabilistic methods to calculate the puzzle's limits.
Which brings us to the math. In 2021, researchers proved the safe threshold was somewhere between n over 60 and n over 4. Basically, they proved that if you randomly place up to roughly 1.6% of the total queens, you can always finish the puzzle. They also proved the threshold couldn't possibly be higher than 25%, a quarter of the board, by using linear programming duality to show how placing queens in a central block totally starves the corners. But then, the 2026 breakthrough by Hugo Møller Nielsen totally changed the game. He systematically constructed a sparse configuration that exploited those diagonal color constraints so effectively it actually lowered the absolute maximum ceiling.
Nielsen came in and proved that if you blindly fill just 21.6% of an infinitely large board, an algebraic deadlock isn't just likely, it becomes absolutely unavoidable. Literally, there's no way out. He achieved this by revisiting that bipartite graph we just talked about and strategically placing a sparse set of queens. He proved that by placing queens on fewer than 0.216 times n squares, he could block a vast number of potential remaining positions. He brilliantly exploited the diagonal alignments to choke off the available space, permanently running the remaining queens out of valid squares. This proved once and for all that the point of no return for this puzzle happened significantly earlier than anyone previously thought.
Now you might be wondering, why does this matter? Well, this isn't just some abstract math trick. Because this completion problem is NP-complete, it serves as the ultimate benchmark to test the reasoning capabilities of modern artificial intelligence frameworks. When a problem is defined as NP-complete, it basically means that as the board gets bigger, the time it takes a computer to find a solution explodes exponentially. Gent and his team proved this about the n-queens completion back in 2017. If you give an AI a board populated with queens below our completion threshold, deciding if a solution exists is trivial. The math guarees it. But the second you cross that line, it becomes a chaotic, completely unpredictable landscape. AI models have to rely on advanced neurosymbolic logic and agentic frameworks just to navigate it. It is literally an obstacle course designed to push the computational reasoning limits of artificial intelligence. And honestly, that is exactly the kind of logic testing we need before we let AI handle complex, chaotic, real-world systems.
So, as we rely on this 170-year-old puzzle to evaluate the smartest algorithms on Earth, it really leaves us wondering, will AI one day crack the absolute mathematical limits of its own test? Think about it. We went from a wooden chessboard in Franz Knock's parlor to translating squares into rainbow-colored graphs to optimizing fractions of a percent in high-level computer science bounds. The gap between the safe threshold and the absolute limit is definitely shrinking. But the mystery? Well, it isn't fully solved yet. And as we continue to build AI frameworks specifically designed to navigate this exact algebraic deadlock, we might just see a machine finally provide the definitive answer to a puzzle that has haunted human mathematicians for generations. What do you think? Are we close to cracking the ultimate threshold?